x to the power of 2/3. Now, I'm going to give you a bit of a hand. We already did some work with x to the power of 2/3, but we did it when it was on the denominator, okay? Remember that too. What I pulled out of it was, it's an even function. It's an even function. So whatever I get on one side, I can get it on the other. That's really good, okay? Yes?
Isn't that the inverse function? Oh, we haven't, don't worry. Thanks.
Stay over here. Okay. Y equals x to the power of 2/3. Does it have any discontinuities? Are there any values that break it? I can put in 0. 0 to the power of 2/3 is still a value. It's 0, in fact. So I'm there, right? Okay, let's just think about what happens as x gets bigger. So I'm getting this kind of shape. Okay, and because it's even, which we noticed before, it's doing that. It has to. It's even. Okay? Can we confirm some of this by getting its derivative? Got a lot of messy one. What's the derivative of x to the 2/3?
2 on 3 root cube root x.
There's that x to the power of negative 1/3 in there, right? Because I took that and I subtracted 1. Okay? Does this fit with what I'm expecting over here?
Yes.
Tell me what's happening as x gets bigger. Tell me what happens.
Decrease.
As x gets bigger, even though it's doing it slowly, the denominator is growing. Do you agree with that? And it's never going to stop growing. There's nothing that stops it, okay? So this denominator is going to get really large. It'll take a while, but it'll get really large. So therefore, I'm doing this thing as well, aren't I? I'm going to approach 0 over here, okay? Like so. But, do you notice? Cube root of x, that appears here, doesn't it? It's an odd function, right? Just like x cubed is an odd function. So therefore, when you start putting negative numbers in here, can you get a cube root of a negative number?
Yes.
Sure can, right? Like say the cube root of negative 27 is negative 3, because it's negative 3 times negative 3 times negative 3. The negatives are okay. So therefore, even though I'm approaching here, really, really small value, over here, I'm going to be approaching, but I'll be negative, right? Because x is negative. So I'm going to be doing something like this. You all right with that? Okay. Last little piece of information. What else can I put on here?
That when the values of x are small, it becomes a really, really large number.
Okay. That goes along with the other piece of information I was thinking. Let's take that. If x is very little, then the denominator is very little, which means the whole number is astronomically large. Okay? Don't forget though, if it's negative, it's astronomically large and negative. If it's positive, it's astronomically large and positive. Okay? So I'll bring that all together, and I'm getting a picture of something like this.
Should we have an asymptote x equals 0?
We should have, and this is what I was getting to. In order to have that, what you're really describing is asymptotic behavior, just without saying there's an asymptote. We kind of already knew that because x is on the denominator, yes? So therefore it can't be equal to 0. Does this derivative gel with the graph that we drew?
Yes.
It does, doesn't it? Do you see? It's not always an increasing function. Over here it's decreasing, dropping like a rock until you get to 0. It's vertical as well. In fact, I should probably make mine a bit steeper. And then as you transition, x is positive, it shifts into increasing because this guy is positive, right? If I go back to my green gradient, right? Negative, 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 positive, 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 positive. Okay? So, by the way, one last little piece. What kind of symmetry? What kind of symmetry? Okay, so we'll do some formal stuff with that later. What do we get from all of this? Okay, these points here, 1, 2, 3. They happen to all be at the origin because I chose some really nice, easy values for us. These are what we call critical values. Okay, the important thing that you've been noticing here, 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 is those discontinuities in the derivative. That's really the key, right? Discontinuities in the derivative. Some textbooks will also expand this definition of critical values to include places where the derivative is 0 as well. I don't think that's really necessary because we have perfectly fine language for describing what happens when the derivative is 0. What do we call those? Stationary points, right? Like I said, the definition's not quite as fluid, not quite as rigid. So I think this is a really good way to approach these. Different interesting things happen, right? So you've got this thing happening here, piecemeal function, no surprises. This is not a horizontal point of inflection. It's a vertical point of inflection. I think someone asked about this before. Horizontal kind of implies you can have vertical. That's vertical. This thing is not a point of inflection, but something else interesting happens there. It has its own name. It's called a cusp, right? Where it has that sort of sharp cutting sort of bit there, right? So these are all different, very different things, right? And that's what I mean by like they all come under this heading. Because discontinuities in the derivative, it's like, well, I don't know what it is. So different things can happen. These are all very different things, but they share this idea in common. Okay, does that make sense? These critical values, like I said, when the textbook talks about it, I'm 95% sure the particular textbook you guys are looking at includes when the derivative is equal to 0. That's fine. The question will tell you what to look for. These are the really important ones, but sometimes it will also say, and include the stationary points in that as well, okay? Because something interesting is happening. That's all critical means.